Hello, in this video, I'm going to be reviewing the tensile testing practice worksheet that is in your lab manual. So to begin, I'm going to share my screen. And now you can see my worksheet. I've got this elevated on a stack of books so that it's a little closer to the document camera. And hopefully you can see it reasonably legibly. So in number one, we've got this stress strain curve for a particular type of aluminum. And in part A, we're asked, what is the modulus of elasticity for 2011, aluminum 2011? So remember the modulus of elasticity, AKA elastic modulus, AKA Young's modulus, is the slope of this linear portion right here. So we just have to calculate the slope of this linear portion of the curve right here. You can pick pretty much any 2 points on here in the linear portion. When you have some toe compensation like this, you should make sure not to pick the origin, because if the origin is one of your points, then you're getting the slope of something like this curve right there, that line, which is not the slope of this line right there. So the 2 points I have picked are at this point at a stress value of 50,000 PSI, and this point right here at a stress value of 10,000 PSI. Then I drop a dotted line down, and I think that it drops down to a strain value of about 0.043. And I'm using kind of some eyeball, guesses right there, but I think that's pretty close. And right here at a stress value of 10,000, I drop a line down, and I think that's about a strain value of 0.024 inches per inch. So those are my 2 points. And to calculate the slope, I take the rise over run, or the change in stress divided by the change in strain. So my change in stress is 50,000 PSI minus 10,000 PSI. And my change in strain between those 2 data points is 0.043 inches per inch minus 0.024 inches per inch. And when I plug those into my calculator, my result is 2,105,260 PSI, or about 2.1 million PSI, which is probably pretty realistic for most kinds of aluminum. So that's probably in the right ballpark. Part B says, what would happen if a 10,000 pound load was applied to the specimen on the right? That's this one that was tested if it was made of 2011. All right, so that's this specimen right here. So we want to know what would happen. Notice that we're trying to calculate what would happen with a 10,000 pound load. That's a force. Notice this is in stress. So we can't directly take 10,000 pounds and see where it would fall up here. We got to do a little bit of calculation first to find the stress that would result from a 10,000 pound load. So let's do that. We want to calculate the stress from 10,000 pounds force on this part. Stress is force divided by area, so I have to know the area first. So calculate the area. That's the cross-sectional area of this part. Area of a circle is pi r squared, and if the diameter of this section is 0.25 inches, then that makes the radius 0.125 inches. That's 1/8 of an inch. We square it and then multiply it times pi to find the area is 0.0491 inches squared. Now we can take that area, plug it into our stress equation for A. So we take 10,000 pounds force divided by that area that we just calculated, and we get a stress of 203,720 PSI. So that is a stress value that we could compare up to this because it's the same material. And you can see 200,000 PSI is way above anything that is on this plot. So 200,000 plus PSI is way above the yield stress, and it's way above the ultimate tensile strength. So we can't solve this problem except to say that it's going to break. Not only will we have plastic deformation because the stress value is above the yield stress, but it's above the ultimate tensile strength. It's way above the ultimate tensile strength. So it's very safe to assume that if you apply a 10,000 pound force load to this specimen made of that material, then it's going to break. That's a very safe statement to make. What it says here, just in case you can't read it, it would exceed the yield strength and the ultimate tensile strength, and so therefore it would break/fail. So that's what it says there. In part C, it says if a 1,000 pound load was applied to the product on the right, this specimen, how much would it stretch? All right, so we're trying to find the change in length is what we're trying to get to. And what do we know right now? We know the elastic modulus. We know the force that is applied to it. And so we need to use our equations that we've talked about in class for stress and elastic modulus and strain to calculate what is the change in length of this part. So it's kind of like a three-step process. First of all, by using the force, that's this 1,000 pound load, we can calculate the stress. And then once we know the stress, we can use that and the elastic modulus that we know from part A to find the strain. And then once we know the strain and we also know the dimensions of the part, we can use that information to find the change in length. So this is like a three-step process right here. First step, like I said, is to find the stress. Stress is force divided by area. The force it says is applied is 1,000 pounds force divided by the cross-sectional area, which we've already got from part B, 0.0491 inches squared. So our stress, when I apply 1,000 pounds force, is 20,372 PSI. So once you get that stress value, you should remember to check and make sure that that value is less than the yield stress. Because if it's less than the yield stress, we can use the relationship between stress and strain given by the elastic modulus. If not, then we can't use that relationship because it doesn't apply and we can't solve this problem. But fortunately, 20,000 some PSI is well under the yield stress. The yield stress here is probably, I don't know, 52,000 PSI, something like that. So we're well under the yield stress, so we can proceed. Now that we know the stress and we already know the elastic modulus from part A, we can use our elastic modulus equation and rearrange it to find the strain. And we find that the strain is equal to the stress divided by the elastic modulus. So that's 20,372 PSI from up above here, divided by the elastic modulus from part A. And that gives us a strain value of 0.00968 inches per inch. When you're calculating strain, you need to keep a fair number of significant figures because these tend to be relatively low values. So as you can see, I've kept 5 sig figs here. I'll round a little bit in the final answer, but intermediate to the problem, in the problem, keep a few more sig figs than you think is really necessary. So that's our strain value. And then we can use our definition of strain. Strain is change in length divided by original length. Rearrange that to find the change in length because we know the strain now from the previous step. And we know the original length from the detailed drawing over here of the specimen. This is the gauge length, and the gauge length here is 1.25 inches. So I find that the change in length is the strain times the original length, which is 0.00968 inches per inch. Remember to keep your units all the way through this problem, times the gauge length, which is 1.25 inches. The inches in the denominator here and the numerator here cancel out, and I'm left with 0.012 inches for an answer. So that is the first page of the worksheet. And then if I go to the next page, I've got a new specimen called the new connector, and it's made of the same material, which means I can still use all those relationships, the elastic modulus, the stress strain curve, and everything from the previous page, but I've got some new dimensions and maybe I'll apply a different load to it. So now I've got a new specimen and I apply a 5,000 pound load is applied in tension to this, and we want to know how much it will stretch. So this is very much like the last problem that we did. In fact, it's almost identical to the last problem that we just finished talking about. We're going to calculate the stress because we know the force and we can find the cross-sectional area. And once we know the stress, we can use the elastic modulus relationship to find the strain. And then once we know the strain, we can use the definition of the strain to find the change in length, which is how much it will stretch. So that's our plan here. So first I have to know the cross-sectional area in order to calculate the stress. So the area, once again, is pi r squared. The diameter here is 3/8 of an inch, 0.375. And so the radius is 0.1875 inches. So square that, take it times pi, and you find that the area is 0.1104 inches squared. Now I can calculate the stress by taking this force divided by this cross-sectional area, and I get a resulting stress value of 45,290 psi. Remember, at this point, when you calculate the stress, you must check to see if it's less than the yield stress. And in case you don't remember that, here's our yield stress, probably at about 52,000 psi. The stress that we just calculated was about 45,000 psi. So we're definitely still less than the yield stress, so we can proceed. Now that we have the stress, we can use the definition of the elastic modulus to find the strain, rearranging the definition of the elastic modulus a little bit to find that the strain equals the stress divided by the elastic modulus. So plug in this number that we just calculated for stress, plug in the value for the elastic modulus that we calculated in the first problem on the first page. It's the same material, so it has the same elastic modulus. So this number still applies. So I find that the strain is 0.0215 inches per inch. And then the very last step is to use the definition of the strain and rearrange it to find the change in length. That's going to be equal to the strain times the original length. The strain we just calculated up here, take that times the original length, which is the gauge length of the specimen, which is 1.5 inches. Multiply those together, your inches cancel out, at least some of them do, and you're left with final units of inches, and the number is 0.032 inches. All right, so that is how much this part will stretch when a 5,000 pound load is applied to it. And it says here, just remember, remember this calculation is only true as long as the stress is less than the yield stress. We can do this type of calculation so long as this stress is less than the yield stress. All right, then the next problem says what load, that means pounds force, in tension will be needed to cause the new connector, this part, to stretch by 0.01 inches. So that's the change in length. And we're trying to find the force. And it says it's the same material. So all the dimensions from the previous problem and the elastic modulus from before, that all still applies. And we're trying to find what force will cause this amount of change in length. So this is kind of like the opposite situation from the previous problem. In the previous problem, we were given a force and we're trying to find how much will it stretch, the change in length. In this one, it's the exact opposite. We're given a change in length and we're trying to find how much force is required to cause that amount of change in length. So we're kind of going to go backwards here. So using the change in length and the original length, that's the gauge length, we can solve for the strain. So strain is change in length divided by original length, 0.01 inches divided by the original length, the gauge length, which is 1.5 inches. That is 0.0067 inches per inch. Now that we know the strain, and we also know the elastic modulus from before, remember this is the same material, so therefore we can use the same elastic modulus because it's an intrinsic property. So we can use the definition of the elastic modulus and rearrange to solve for stress. The stress is the strain times the elastic modulus. So there's our strain from above, and there's our elastic modulus from previously. Multiply these two together, and you get a value of 14,035 psi. So that is our value of stress. So we need to check to make sure it's less than the yield stress. And so if you don't remember, you can go back to check your stress strain curve. And we're talking about 14,000 psi. It's about here. So we're well under the yield stress. So that's good. we can proceed and carry out the calculation because that value is less than the yield stress. So next, we can calculate the force because we know the stress now, and we know the cross-sectional area from the previous problem. So rearrange this equation for stress to find that the force equals the stress times the area. Plug in the value for stress that we just calculated. Plug in the value for the cross-sectional area that we previously calculated for this part. It was up here. And I have 14,035 pounds force per inch squared. That's PSI. That's the stress. Times 0.1104 inches squared. So your inches squared cancel out, and you're left with 1,550 pounds force. All right, and then the very last one is actually probably the easiest. It says what load, that is what force, will cause the new connector to reach the yield stress, its yield stress, assuming it's made of that exact same material we've been talking about this whole time. All right, so this one's actually only one or maybe 1.5 steps. You do have to know what is the yield stress. So that's not even really a calculation, but you have to look back here and say for this material, what is the yield stress? So I would say it's about 52,000 PSI. That's pretty close, I think. So that's the stress that is the yield stress. So that's the stress that we're trying to calculate the force will cause. That was a weird way of saying that, but we're trying to calculate what force will cause that stress, the 52,000 PSI stress. So there's our stress. There's our equation for stress. We can rearrange it to solve for the force. And we find that force is equal to the stress times the area. We just said that the stress that we're trying to achieve in this problem is the yield stress, which is 52,000 PSI, which is pounds force per inch squared. And our area of this specimen up here is the same one from the previous problems. So it's 0.1104 inches squared. So your inches squared cancel out, and you plug that into your calculator and you get 5,741 pounds force. That's the force that when you apply it to that specimen, that will cause it to reach the yield stress. I hope it was helpful to review that worksheet. Let me know if you have any questions, and I'll see you in the next class.